In this lesson, we're going to learn how to incorporate the idea of resonance into our Lewis structures. Resonance is a way of dealing with multiple bonds when they can be equally located in different positions within the Lewis structure. So let's take a look at an example and look at a covalent compound, a molecule, that exhibits the idea of resonance. We're going to look at SO3. This is the molecule sulfur trioxide. This is not the sulfite ion. The sulfite ion would have to have a 2 negative charge. So this is a neutral covalent molecule, sulfur trioxide. So as you can notice, we've identified the central atom, and we have a single bond between the central and the surrounding atoms. We've counted up the valence. We have sulfur from group 6A and oxygen from group 6A. So we have 4 elements, all from group 6A. 6 times 4 is the valence of 24. So following the rules, we've identified the central. We tried a single bond between the central and the surrounding. We now need to make sure our surrounding atoms, in this case the oxygens, have an octet. So let's add in our lone pairs. Let's add in our 3 sets around each oxygen. Upon doing so, we now have each oxygen with an octet. Now if you count up the surrounding atoms, which in this case we have 3, and if each has 8, counting the ones that are being shared with the sulfur, you have 24 total. If you had any extra electrons, they would always go on the central atom. In this case, we have no extra electrons. We've used all 24. So sulfur, the central atom, needs an octet. It needs 8. So we'd have to say here that sulfur is electron deficient. You may recall that when a central atom is electron deficient, you get to incorporate in a multiple bond. So we need to add in a double bond between one of the oxygens and that central atom, between oxygen and sulfur. And when we add in that multiple bond, we're going to reduce the lone pairs, in this case from 3 down to 2. So I'm going to change the farthest left-hand bond. I'm going to change that single bond between the oxygen and the sulfur. I'm going to change that to a double bond. So now, if we change that single bond to a double bond, notice the lone pairs went from 3 lone pairs down to 2 lone pairs. Each of our surrounding atoms now has an octet. They each have 8. Sulfur in the middle also has 8. So this looks like a good Lewis structure for SO3. The only thing you may be wondering is, why did I pick the left oxygen to add the double bond? Why didn't I pick the bottom oxygen or perhaps the right oxygen? They all seem to be equal locations where that double bond could exist. The reality is, I could have picked any of the oxygens. I just randomly picked the left oxygen. So if there are equal positions where a double bond could be located, then you have to show resonance. And what that means is you have to show 3 structures where the double bond could be located. It would look like this. So SO3 has 3 resonance structures, showing that the double bond could have been equally located with any one of those 3 oxygens. So you may ask the question, well, of the 3 that we've now drawn, which one is correct? Well, in all honesty, none of them are correct. None of them individually represent the true bonding in SO3. But if you have all 3 depicted and you have the arrows between them, this represents resonance, and the true answer is an average of these 3. So when you have the ability to depict resonance, as we do here, where you have equal positions, where a double bond can be equally located, you need to show a Lewis structure for each one of those resonance structures, and then realize that each one individually is not correct, but all 3 of them averaged together would be truly what the bonding would be represented in a molecule that exhibits resonance.